Welcome everyone. In this video we are going to be working with work and energy. If you are not familiar with these concepts, you can feel free to watch one of my previous videos where I explain the basic principles of work, energy and the work energy theorem. We're going to start off with an easy example, okay? So a car of mass 2000 kilograms accelerates on a horizontal road from 6 meters per second to 18 meters per second in 12 seconds. And we are going to try to calculate the work done by the engine in the 12 seconds. Now we first need to analyze this question, right? So we have a car that's moving and it has an initial velocity, right? And it has a final velocity. And we have a time over here. Okay, so let's use that information to get to our answer. The first thing you want to do is to list your variables. That means you look at the question and you identify what information are you going to be working with and what information do you need to pull from the question. And from the question, these are the variables that we've identified. You have your mass, an initial and final velocity, and your time. Okay. To answer this question, we are going to need to use the work energy theorem, which in equation or symbolic form looks like this. The net work done is equal to the change in the kinetic energy of an object. And if we expand kinetic energy, it looks like this. Or the change in kinetic energy rather, half mv squared minus half mvi squared. Right, and to make it simpler, we can take this factor out. And we can say that it's equal to half m, open brackets, v squared minus vi squared. Right, now this is not necessarily the work energy theorem. It comes from here. So please make sure you write the original one in your answering. And so what does this look like when we apply it to the question? Okay, as you can see now, I've written out my equation and now I'm going to substitute. And when I substitute, it's going to look like this. 2000 is the mass. Okay, my VF, my final velocity is 18, my initial velocity is 6. And I'm going to plug this into my calculator now. I just wanted to show you what this looks like on my calculator because I know that sometimes brackets and things can get confusing. So just make sure that you have everything in brackets using this 1/2, or you can also say multiplying everything by 0.5, it's also fine. And this is going to give us an answer of 288,000 joules, and this will be your final answer for this particular question. The next thing we're going to be looking at is what is the power of this specific engine, and to do that we are going to look at the meaning of power. Right, so we know that power is the rate at which work is done, right? It is the rate at which work is done. Now the key phrase here, or one of the key phrases, is rate, because we know that the rate is related to a very special mathematical function, and that is to say that power, symbolized by the capital letter P, is equal to work divided by time, with delta T. Okay, and so this is where we get the idea of rate from. So to answer this question, you can see how if you have a value for W, if you have a value for work, you can now, and if you have a value for time, you can calculate the power. And let's just do a quick dimensional analysis here. We know that work is measured in joules. We know that time is, the SI unit for time rather, is in seconds. And so technically, power is measured in joules per second. But we have a definition for this, and we call this a watt. Okay. So what does that look like in our specific problem? If we write out the equation, right, and we're going to substitute now, and we see that my answer here is 24,000. Now if we look at the units, that is in joules second, a joule per second is called a watt, and that is my final answer. The next question we're going to do is from November 2019, and this is question 5. And it has to do with work and energy. It says an object of mass 1.8 kilograms slides down a rough curved track and passes point A, which is 1.5 meters above the ground. So this diagram helps you to visualize what's happening. And then it's approaching the ground, or in other words, the initial velocity there is 0.95, and the final velocity, the velocity that it reaches the bottom with, is 4 meters per second. Right, so the first question is to define a conservative force. As you know, you have to look in your metric guidelines for that. We'll do it here as well. So a conservative force is officially defined as the force for which the work done is independent of the path taken. Now this has some very serious implications. This means that no matter where your object is moving towards, the force done there will be the same. Right? It's normally your field forces that your conservative forces, such as the gravitational force. And that's what we're going to be working with today. And so the question here, 5.2, is to name the conservative force that's acting on this object, right? So you know that this is experiencing frictional force, but there's also a weight that's pulling it down. And as we know, weight is caused by the gravitational force. And so the answer for this here is going to be weight. The third question is mechanical energy conserved as the object is sliding down from point A to point B? And this is where we can look at the diagram and the description of the question. So it uses it describes the curved track as rough. Okay, so as we know, when there's a rough surface, there is a lot of friction involved. And it also doesn't say that it's an isolated system. Okay, and so we can also see even from the picture that they've drawn these squiggly lines, and that indicates that this is a rough surface, and it reminds you that friction is present. And so the answer here will be that no. You have to say no in the exam question, in your answer, because that's the first mark, and the reason will be the second mark. And the reason can be multiple things. You can either say that, look, there is going to be friction here, or you can say that the system is not isolated. And those will be two acceptable answers for this question. And now let's do these two calculations. The first calculation is to calculate the gravitational potential energy when it is at point A. And the second is to use the energy principles to calculate the work done by the frictional force on the object as it slides from point A to point B. Right, the equation we're going to use here is E subscript P is equal to mgh. And we know this is going to be equal to the mass of the object, which is 1.8, multiplied by the gravitational acceleration of the Earth, which is 9.8, multiplied by this height over here. So this height is given to us to be 1.5 meters, right? And that gives us an answer of 26.46 joules. And so this is the potential energy of the object when it is at point A. So in other words, this sum or this calculation is indicating to us that this is how much energy the box has when it is raised to a level of 1.5 meters. When an object of this mass is raised by this height, this is the amount of potential energy that it has. That is what this calculation is showing. Now let's do the next question. The next question is using energy principles, calculate the work done by the friction as it slides from point A to point B. So in other words, when the box is moving along this path, there is work done, right? Or in other words, there's a transfer of energy that is happening. And the thing that is causing the transfer of energy is the frictional force. So that's why they word it in this way. They say the friction, which is a frictional force, is doing work. Right? And you want to calculate the value of that work. And that's what this means. Right? So as the box moves here, it's going to experience frictional force. And so the frictional force itself is going to be performing work, you can say. Okay, and we're going to calculate the value of that work now. So we know that friction is a non-conservative force, right? Subscript NC. And so we write this to indicate the work done by any non-conservative force. And that's exactly what we're trying to find, isn't it? And we know, and this is also on our formula sheet, that the work done by non-conservative force is equal to the change in the mechanical energy, right? So, in other words, in an isolated system, we know that E mech, or the change in E mech, is naught. In other words, that there is no change in mechanical energy if the system is isolated. However, if your system is not isolated and you do have non-conservative forces, then this is not, so if it's not isolated, that is not zero. In fact, it has a value, and that value is the work done by your non-conservative forces. And so if we expand E mech here, this is what it looks like. And we know that E mech is the sum of your kinetic and potential energies. And if you expand that further, this is the factoring out and expansion that you're going to get. And so what does this look like when we're trying to approach it and use it to solve this problem? So I'm going to substitute the values that I have into here. And I want to quickly discuss where we got them from. So 1.8 is the mass of the object. 4 is because 4 meters per second is the value of the final velocity that we were given. 4 meters per second is the value of the final velocity we were given. 0.95 is the value of the initial velocity we were given. Over here, we have those same values and obviously a gravitational constant. Then the 0 over here is the final height, right? See that? Because the height at which the box is moving at 4 is 0, right? This is the ground. Okay, because it gives us this reference frame here, the ground. So that's why I'm inserting a 0 there. And I'm subtracting the initial height, which is 1.5, right? So even though obviously, you know, we're assuming this is a positive direction, I have to multiply this by a negative 1.5. And the reason being is because I have subtracted this initial height because I am dealing with a change in potential energy. And the reason why it's so important to get this step right is because you're going to get your negative answer, which is the correct answer for this particular question. Now this final answer, this final question over here is very interesting. It says, what is the value of the net work done on the object as it slides from point B to point C? And it says here that surface BC is frictionless. Always be careful for these in-between clues that they give you in between the questions. So let's look what's happening here. This is actually very interesting because it's a Newton's first law principle. And that if it's a frictionless, surface, right, then according to Newton's first law, this is an isolated system. There's nothing going to stop this motion from, nothing is going to increase it, right? And if net is equal to naught, and there's no acceleration, and nothing is going to increase it or decrease the speed, this velocity. And so in theory, this should continue in a straight line because there's nothing going to be slowing it down. And so this motion will be the same. And so what we find there is that your VF will be equal to your VI, right? Because this is what it means to travel at a constant velocity. And so if you are doing, this equation, if you are doing this, and you're trying to find out right, because these numbers are the same, this factor is going to be 0, and so your whole product is going to be 0 joules, and so that's why this is your final answer.